Why do engineering designs fail? Is it because engineers make calculation mistakes? Is it because the technology doesn't work? Or is there something more fundamental? Interestingly, many engineering designs fail even when the technology itself works. A product may perform exactly as intended, but still be too expensive to manufacture, too difficult to use, unreliable in the real world, or simply something that customers do not want. In this module, we will look at why this happens. Understanding why designs fail is an important first step toward understanding how we can design better. Imagine that you have designed a new washing machine. You build a prototype, test it, and everything works exactly as expected. The motor runs smoothly, the drum rotates correctly, and every engineering calculation is correct. Does that mean you have a successful product? Not necessarily. What if the product is too expensive to manufacture? What if it takes twice as long to assemble as competing products? What if customers find it difficult to use? Or what if it works perfectly in the laboratory but starts failing after only a few months in real-world use? In all of these cases, the engineering design has technically worked, but the product has still failed. This is one of the most important lessons in engineering. A successful engineering design must succeed not only technically, but also economically, in manufacturing, in reliability, and in satisfying the needs of the people who use it. When people hear the word failure, they usually think of a product that simply doesn't work. But in engineering, failure has a much broader meaning. A design may fail technically if it cannot perform its intended function. It may fail functionally if it is difficult to use or does not satisfy the user's needs. It may fail in manufacturing if it is too difficult, too slow, or too expensive to produce consistently. It may fail economically if the production cost is so high that the product cannot compete in the market. A product can also fail because it is unreliable, breaking down frequently during normal operation. Even if everything else is acceptable, a design fails if it creates safety risks for the user. And finally, a technically excellent product can still fail in the market if it doesn't solve a real customer problem, or if people simply don't want to buy it. Successful engineering means balancing all of these dimensions, not just making the product work. One of the biggest reasons engineering designs fail is surprisingly simple. We solve the wrong problem. Imagine we want to design a washing machine for a rural community. We may assume that customers want more automatic functions, more washing programs, and advanced electronic controls. So we design an excellent, high-technology washing machine. But what if the real needs are completely different? Perhaps customers need a machine that is affordable, uses less water and electricity, is easy to repair, and can operate reliably under difficult environmental conditions. Our engineering may be excellent, the product may work perfectly, but we have solved the wrong problem. This type of failure usually begins before engineering even starts, when we make assumptions instead of deeply understanding the user and the real operating environment. That is why the thinking stage of the TEM design spiral is so important. Before asking, how do we design the solution, we must first ask, are we solving the right problem? Once we understand the problem, there is another common mistake. We fall in love with the very first solution that comes to mind. As engineers, we naturally enjoy solving problems. So when a promising idea appears, we often become excited and immediately start designing. But the first idea is rarely the best idea. Imagine designing a new washing machine. Your first concept may be a fully automatic, feature-rich product. Without exploring other possibilities, you begin detailed design. Later, you discover that a simpler, lower-cost design would have been easier to manufacture, more reliable, and better suited to the customer's needs. Now the project requires redesign, causing delays, extra cost, and wasted effort. Great designers don't stop at the first idea. They explore many alternatives, compare them objectively, and only then commit to the best solution. In the TEM design spiral,
Exploring multiple concepts during the thinking stage dramatically reduces expensive changes later in the project.
Another common mistake is starting detailed engineering too early. Once we have a promising concept, we may immediately begin detailed CAD models, engineering calculations, component selection, and technical drawings. But there is an important question. Have we actually proven that the basic concept will work? Imagine spending weeks designing a washing machine mechanism in detail, only to discover during prototype testing that it creates excessive vibration, requires too much power, or is simply too expensive to manufacture. Now, much of that detailed engineering work must be repeated. A better approach is to validate the important assumptions early. Use simple calculations, simulations, basic models, and low-cost prototypes to answer the critical questions first. Then, once we have confidence in the concept, we can invest in detailed engineering. The lesson is simple. Prove the concept before you commit to the details.
Many engineering designs look excellent on the computer screen. The CAD model is beautiful, the calculations are correct, and every component fits perfectly in the virtual world. But then, the design reaches the factory. The manufacturing engineers immediately identify problems. Some parts require extremely tight tolerances that are difficult to achieve consistently. Others require expensive tooling or complex assembly procedures. Some components take too long to manufacture, while others are difficult to inspect or repair. The design may still work technically, but it is now too expensive, too slow, or too difficult to produce. A successful engineering design must be designed not only for performance, but also for manufacturing. This is why experienced companies involve manufacturing engineers from the very beginning of the design process. A good engineer doesn't ask only, will this work? They also ask, can we manufacture it efficiently, repeatedly, and at a competitive cost? That question often determines whether a product succeeds or fails.
All of the failures we have discussed so far lead to one common outcome. We discover important problems too late. Perhaps we skipped concept validation. Perhaps we didn't explore enough alternatives. Perhaps we ignored manufacturing or user feedback. The result is the same. Major problems are discovered only after detailed design, prototype construction, or even after production has begun. At that stage, every design change becomes much more expensive. A small design modification that would have taken a few hours during the concept stage may now require redesigning drawings, modifying tooling, rebuilding prototypes, repeating tests, and delaying production. The later a problem is discovered, the more people, money, and time are affected. That is why successful engineering teams continuously ask one question throughout the project. What can we test today instead of discovering tomorrow? The purpose of prototypes and experiments is not to prove that we are right. Their purpose is to discover, as early as possible, where we are wrong. Early learning is the cheapest form of engineering.
Why is discovering a problem late so dangerous? Because the cost of changing a design increases dramatically as the project progresses. During the concept stage, changing an idea may require nothing more than changing a sketch or updating a few calculations. During detailed engineering, the same change may require new CAD models, drawings, calculations, and component selections. After a prototype has been built, the prototype itself may need to be modified or rebuilt. And once production has started, a design change may affect tooling, suppliers, inventory, assembly procedures, testing, and even products that have already reached customers. So the exact cost multiplier will vary from project to project, but the principle is clear. The later we discover a problem, the more expensive it becomes to correct. This is why good engineering is not about avoiding all mistakes. It is about discovering mistakes when they are still small, inexpensive, and easy to correct. Find early, fix early, learn early.
So, how do good engineering teams avoid these failures? They do not rely on getting everything right the first time. Instead, they follow a disciplined process that helps them discover what they do not yet know. They begin by understanding the real problem and challenging their own assumptions. They explore multiple solutions before committing to one.
They use simple models, calculations, experiments, and prototypes to test the most important assumptions early. They involve users, manufacturing engineers, suppliers, and other stakeholders before major decisions become difficult to change. And when something fails during testing, they don't simply see it as a setback. They treat it as information. They learn, improve the design, and repeat the process. This is the mindset behind the TEM design spiral. Think early, test early, learn early, then invest in detailed engineering and manufacturing with greater confidence.
The TEM design spiral provides a structured response to the failures we have discussed. Instead of treating design as a straight line from idea to finished product, we move progressively through 3 stages: thinking, engineering, and manufacturing. In the thinking stage, we focus on conceptual design. We understand the real problem, explore different possibilities, and select promising concepts. In the engineering stage, we develop the preliminary design. We analyze, calculate, simulate, prototype, and validate the concept. In the manufacturing stage, we move toward detailed design and production. We define specifications, tolerances, processes, assembly methods, and everything required to manufacture the product reliably. But the most important idea is this: within every stage, we explore, create, and evaluate. When evaluation reveals a problem, we don't blindly continue forward. We learn, improve, and iterate. So the design moves forward like a spiral, from a high-level understanding toward an increasingly detailed and manufacturable solution. This is how the TEM design spiral helps us discover problems early, reduce risk, and make better engineering decisions. Let us conclude with the central lesson from this module. Engineering designs do not fail only because of incorrect calculations or technical mistakes. They also fail when we solve the wrong problem, commit to the first idea too quickly, begin detailed engineering before validating the concept, ignore manufacturing realities, or discover important problems too late. The TEM design spiral helps us avoid these failures. At each stage, thinking, engineering, and manufacturing, we explore, create, and evaluate. We learn from the results, improve the design, and repeat the process before moving forward. Good engineering is not about getting everything right the first time. It is about discovering what is wrong early enough to improve it. So remember, think early, test early, learn early, improve continuously. A better design process leads to better products, lower risk, reduced cost, and greater value for the people who use them.